Welcome to our session 2A. I'm Chen from University of Iowa, and I'm one of the new principal investigators in our new HAQAST team. So I'm excited to see all of you here in person. So this session is about improving surface fine particulate matter estimates using satellite data. We will have 4 speakers here, and each one will take 10 minutes talk. And after all of our speakers finish their talk, we will have another 30 minutes to discuss and for Q&A session. Okay, so let's welcome our first speaker, Randall Martin. And he will talk about some research about fine particulate matter.
Thank you. And it's a pleasure to speak with you today about our work on advancing satellite-derived PM2.5 data. This work is motivated by the immense health concerns associated with PM2.5, with millions of attributable deaths each year, deaths that are valued at trillions of dollars, and the large gaps that exist in ground-based monitoring of PM2.5. And thus, a large user community requires information on the distribution of PM2.5. This is by no means exhaustive, but hopefully illustrative of the scale of need. Thus, we'll turn to satellite remote sensing to fill in those gaps, leveraging decades of innovation in probing the electromagnetic radiation emanating from the Earth and applying that information to deduce properties of atmospheric composition, notably here, aerosol optical depth, a columnar optical measure of aerosol abundance. We'll focus on the instruments and algorithms that are in the bottom left to give this overall columnar measure of aerosol optical abundance. The next challenge is to quantitatively relate that columnar optical measure to ground level PM2.5 concentrations. And to that end, we'll turn to the GeoS-Chem model and its high performance configuration, dividing the Earth's atmosphere up into hundreds of millions of boxes and solving for its chemical evolution during transport, and endeavoring to represent the suite of processes involved in that relationship between aerosol optical depth and PM2.5, including composition-dependent hygroscopicity, aerosol vertical profile, and sampling characteristics. You're seeing yellow for mineral dust, blue for sea spray, green for organics, black for black carbon, and red for the sulfate nitrate ammonium system. And a purpose of showing this animation is to emphasize that dynamic nature of these aerosol fields in space and time, such that we'll sample this model coincidentally with every individual retrieval from each one of those different instruments and algorithms, and calculate that local time and space varying relationship of aerosol optical depth with ground level PM2.5. Given the importance of that modeled relationship on aerosol optical depth with PM2.5, as well as on aerosol chemical composition and driving the hygroscopicity of these particles, we then need to evaluate that. And to that, we'll turn to a ground-based measurement network, the Surface Particulate Matter Network, that builds upon the well-respected sun photometer network of AeroNet, and in densely populated areas of relevance for health, adds a PM2.5 monitor. That monitor contains a removable cartridge that is preloaded in our lab here at WashU, shipped off to each one of those different sites, where it runs unattended for a period of time, cycling through those different filter slots, avoiding a traveling blank. Upon completion of sampling, the operator returns that cartridge to our lab for analysis of the chemical composition of PM2.5. The default instrumentation package also includes a nephelometer for high temporal resolution and measurements of aerosol scatter. These measurements offer information, empirical data on the relationship of aerosol optical depth with PM2.5 that are underpinning satellite missions, such as Maya's satellite mission to be launched next year, as well as providing information on the chemical composition of PM2.5 and its relationship with sources. So we'll apply these data to confront this model on the relationship of aerosol optical depth with PM2.5. But despite all the advances we might be able to achieve, bias will remain. So our next step is to use a data-driven approach to predict the bias between our geophysical satellite-derived PM2.5 inferred from those prior algorithms, and treat ground-based measurement data as truth or labeled data, and apply a convolutional neural network to predict that bias between the geophysical data and those measured data to produce the final hybrid data sets. Completion of those 4 different algorithms then achieves the 27-year record that we have of satellite-derived PM2.5, an example of which is shown here for 2024. The data are striking. They vary from less than 10 micrograms per cubic meter over parts of the United States where we do have serious concerns about air quality. And then they extend out to order 100 micrograms per cubic meter over densely populated areas. More than 95% of the world's population live in regions that exceed the World Health Organization air quality guideline of 5 micrograms per cubic meter. This globally complete information source is being relied upon for a large number of international assessments, as one sees on the bottom. For 2024, we notice continuation of two major trends that we've seen over the last decade. The first is continuation of a global reversal in the burden of PM2.5 as examined by Chen, and showing this tentative decline in this global burden with the transition around 2013. And what we find is that's being continued into 2024 with declines over East Asia, but more prominently now beginning more seriously in the Indo-Gangetic Plain. But the contrast is that we see increases in fire intensity and frequency across both boreal forests or northern mid-latitudes in the western United States, as well as some of the tropical regions, and indeed a doubling of the fraction of PM2.5 exposure from wildfires in the United States over the last decade. This 27-year record of PM2.5 across the United States exhibits a remarkable change in over time. It used to be that there was a maximum in the southeastern United States and minima in the west, but we're seeing this reversal with the real success of air quality control in the east, but with the growing intensity of wildfire frequency in the west. These data are used for national assessments, and notably one that I hope you'll hear about from Tracy Holloway about the American Lung Association and its use of these data for the state of global air that Tracy has been leading. It's been an honor to work with a variety of epidemiologists to examine the association of the PM2.5 distribution with a variety of different health outcomes. And the scale of health outcomes that can be examined indicates that significance due to the systemic inflammation response associated with this PM2.5 and the findings of associations that persist down to very low concentrations with no observed threshold. And thus, this has supported the lowering of the World Health Organization air quality guideline down to 5 micrograms per cubic meter and underpins the US EPA annual PM2.5 standard with over 100 citations of this body of work by the Integrated Science Assessment and its supplement. Looking forward as part of our project, there's obviously immense need to continue to advance and improve these satellite-derived PM2.5. We have 4 major themes to do so. The first is to leverage new advances in satellite remote sensing, notably multi-angle polarimeters with a broad spectral range, such as PACE and Maya, that offer new information about aerosol optical properties, as well as TEMPO, offering geostationary observations across the North America. The GeosChem high-performance configuration offers fine resolution capabilities to better resolve nonlinearities between the satellite observations and ground-level PM2.5. Advances in deep learning offer immense power to consistently represent ground-based measurements while paying careful attention to spatial autocorrelation to which deep learning algorithms are susceptible. And then finally, ground-based measurements are needed to underpin and evaluate and improve these data. We've established a new support team designed to support users of the satellite-derived PM2.5 data and look forward to collaborating extensively across the HAQAST community in this endeavor. There are several posters that I'd like to shout out that you'll be able to see this evening. One examining the diurnal variation of PM2.5, which is important to relate aerosol optical depth at satellite overpass time to a 24-hour average, here led by Yunshin Li. Uxuan Ren is examining the black carbon emissions and finding a global underestimate in black carbon emissions across the global south. Siwen Chen presents information about inferring chemical composition of PM2.5 through deep learning. Wenjin Zhang is examining long-term trends in PM2.5 chemical composition. And Chandler Wells from Tracy Holloway's group, not my own, is leading an exciting area in if your county is PM2.5 monitor as well, representing peak concentrations. So with that, I hope to leave you with the growing utility of satellite-derived PM2.5 data for a variety of applications as inferred from satellite remote sensing, chemical transport modeling, deep learning, and underpinned by ground-based measurements, all of which are needed to support both national and international assessments. With that, let me thank my research group who makes this science possible, and thank you for your attention.
Okay, thank you, Randall. Let's welcome our next speaker, Chili from the Washington University in St. Louis again. And he will also talk about some research about PM2.5.
Thank you for the opportunity. So we all use this EPA figure to compare the size of human hair versus the coarse particles of PM10 and versus the fine particles PM2.5. But I have a question. So this cutoff size, 2.5 micrometer, including the 0.5 realm, is that being too precise? And now is actually a very good time to revisit this question because we have many aerosol size distribution data available now, such as this from the NASA ATOM observation of remote aerosols. And when we look at these blue curves representing wet aerosols and black lines of dry aerosols, we can see that below the 2.5 micrometer as the black line, the division point between the fine and the coarse mode are usually universally smaller in these panels. This means that PM2.5 includes significant coarse mass as a globally ubiquitous feature. Similar conclusions are also derivable from the inversion of columnar aerosols in the globally distributed AirNet network. And this is also well supported by the global size-resolved aerosol model, such as the geoscam TOMAS developed by Jeff Pierce. And what's more important, these coarse mass are dominated by the wind-blown dust, as in brown color, which are much less anthropogenically relevant and very hard to regulate compared to the other species like sulfate in red and organics in green, which are mostly resided in the less than 1 micrometer size range. And in many areas of the world, this wind-blown dust actually makes up more than half of the total exposure in PM2.5, as highlighted by these boxes, which makes the regulation of the already very high PM2.5 pollution over these regions immensely challenging. So PM1 has less coarse mode contamination from wind-blown dust mostly, and they are more anthropogenically modifiable. Some parallel studies in China suggested that PM1 has stronger health relevance to many health endpoints compared to PM2.5. And the cost of ground-based monitoring is similar. And we can also use satellite retrievals of aerosol to estimate PM1 because it also resides in the aerosol scattering sensitive size range. So PM1 is definitely an important additional air quality metric to consider and worth further investigation. What I think fills up the successful PM2.5 research in the past decade is that we started with a nationwide, densely distributed ground-based network. And then we can have this gapless, beautiful map of PM2.5 that supplemented by satellite and other information. And then we can use this data set to support exposure assessment and air quality studies relating that to the health outcome. And this outcome from these researches further motivate us to have more efforts putting into the monitoring and estimation of PM2.5. Can we repeat this successful trajectory for PM1. And the problem is that for PM1, we do not have the ground-based network to start with. But alternatively, there is the PM2.5 chemical composition monitoring network that also facilitate this chemical composition estimated map that is produced by the WashU group, which we plan to use in this study to fill up this PM1 research cycle by providing the first ever estimation of PM1 concentration across the United States. Our PM1 estimation algorithm is considering for each of the PM2.5 component, the concentration as well as the mass fraction in PM1 as the K values in this equation. And we use all accessible observational and model information to constrain these K values for each component. The first piece of observational information is from the collocated daily PM2.5 composition from the two well-established ground-based network and the collocated surface PM1 composition using aerosol mass spectrometer technique that is nearby. And this table summarizes all the collocations we get using these two data sources, which are representative of many locations in time periods. And this is an example of a collocation near New York in 2009, where we have the PM1 data on the above and the PM2.5 data and below. And more data are supported by the early EPA campaigns that is conducted over many metro areas of the United States, where we have this Moody instrument that can provide size-resolved chemical composition of particulate matter in different cities of the globe, of the United States, such as this example for sulfate in Atlanta. With that, we can calculate the PM1 and the PM2.5 components from the same sample, and we have all this data that represents a lot of more cities across the United States. And this left figure with 4 panels summarizes the scatter of this PM1 component versus PM2.5 for 4 major PM chemical composition, where we can see that a tight linear relationship can well describe this PM1 versus PM2.5 component mass fraction, so that we can use the fitted linear line, the slope, to describe the K value as the mass ratio summarized in the right table. And for the remaining 3 major components of PM2.5, they contribute less primarily to PM1, and we don't have a lot of observational information. We use the literature, we use the fixed number that are obtainable from literature and used by conventional models to constrain those mass ratio. And we find that by evaluating versus independent PM1 measurements, this data set overcome the scarcity of this direct measurement and have a great agreement versus this independent PM1 data. And importantly, we find better agreements of this approach versus observations from gravimetric analysis approaches as highlighted in the box compared to the other more indirect and inspecific approaches. So with this validated data set, we can now have generated the first map of PM1 distribution over the United States for 2022. We also can estimate the uncertainties per pixel of this concentration, which considers the uncertainties of the estimated component as well as the uncertainties of the mass ratio on the right map. We can see enhanced PM1 over the wide eastern United States, where we do know there are intense and persistent PM sources. We can also see that there are sporadic high enhanced PM1 over the remote western areas, corresponding to occurrences of wildfire in 2022. And more importantly, we see much enhanced uncertainty on the right map of this PM1 over these fire-prone areas. This is because our cross-validation suggested that there is reduced agreements versus observed organic matter and black carbon in our concentration or component estimates, which dominates the PM1 in these fire-prone areas and elevated this uncertainty estimates. This highlights the future endeavor directions to further improve the constraints of estimated fire PM and components. And finally, with this data set, we can now calculate the population-weighted PM1 time series as highlighted in the numbers in the center of these pie charts, and with the colors indicated the component contributions in each year. With the decrease for both PM1 and PM2.5, a noticeable phenomenon is that the contribution of dust in yellow and sea salt in blue has enhanced for PM2.5, mostly in recent years, whereas this enhancement of this contribution is less noticeable for PM1. This is the population distribution against this fraction of dust and sea salt in PM1 and in PM2.5 for the last 5 years in our data set. We can see pronouncedly more populations associated with the significant PM2.5 mass contributed by dust and sea salt relative to PM1. So we are now in a moment that future activities to regulate air quality would be more effective for PM1 than PM2.5, highlighting the stronger urgency to investigate the possibly differentiable health impacts of these two metrics. So in summary, motivated by the potential of PM1 maybe being an important additional air quality metric, here we produced the first ever PM1 data set for United States. And we hope that this meeting would be the right platform to promote this collaboration and promote this research cycle by engaging more application of this data set. Thank you all for your attention.
Thank you, Chi. Yeah, let's welcome our next speaker, Sarah Kroening from the Children's Health Alliance of Wisconsin, and talk about some application in the health. Thank you.
Okay. All right, good morning, everyone. Thank you for having me speak here. My name is Sarah Kroening, and I'm here on behalf of Children's Health Alliance of Wisconsin. So we are part of the Children's Hospital System, and we are kind of the face to work with the community to try to prevent our children from getting to the hospital. So we have a unique opportunity. And I am the program manager for Love My Air Wisconsin, which is an air quality monitoring and no idle campaign program. And we're partnered with schools and organizations focused on youth. I'm here today to share how a youth ministry group is raising awareness about air pollution among their community in Milwaukee. So the inspiration has really come from meeting with Pastor Mary Martha through a shared partnership of a local public school, Hopkins Lloyd. And they've been a long-standing partner. They support events that school will host at the church. And then the nurse that was working at Hopkins is now the nurse at HAQAST. So lots of really pretty amazing connections. So both Hopkins and Tabitha Lutheran Church are in Milwaukee's 53206 zip code. Oops. And this is a neighborhood that faces significant social, economic, and health-related burdens. 53206 has one of the highest rates of asthma ED visits, and they have historically been at one of the highest risks for particulate matter exposure. And yet the community remains determined and hopeful. This church specifically has 450 members, and on Sunday they have an attendance about 125 members. So their commitment to faith and service is truly inspiring, and many members have been coming to HAQAST for generations. I would like to introduce you to Amika, Amira, and Laquan. They are all high schoolers who have been attending Hepatha Lutheran Church their entire lives. Amira is on the far left, and she is a senior in high school. She wants to be a pediatrician. Amika is her sister. She's in the middle, and she's a sophomore in high school and is focused on her studies. And then Laquan is a junior, and he is interested in career with technology. And they are serving as youth apprentices at the church. And so they have many different roles, but the program is really focused on leadership development and growth in potential for young persons of color who have a faith calling to help them explore their role in serving God, leading in the church, and serving others while stepping into their potential. So it's more than just a job. And that was from Pastor Mary and what she highlights as seeing the importance of their work. So through knowing Pastor, through the Hopkins-Lloyd connection, she was really excited to bring air quality into the focus with those youth apprentices. So we started our project by talking about the area around Hepatha and Hopkins-Lloyd and discuss what they knew about air pollution. So as you can see on this map, there are 3 main roads that meet right at the corner of Hopkins, which is the elementary school. Be able to see the mouse. Yeah. So here's the Hopkins School. You can also see in this picture, it's a lot of cement, a lot of blacktop. And then there's 2 highways. Oh, it got cut off, but there's 2 highways. So there's this one, and then over on that side, there's another pretty main highway that is used often. So we discussed the amount of green infrastructure, traffic, and factories. And while they really don't identify as many, I'm losing the track of the mouse. Sorry, you guys. Okay, thank you. So they weren't really sure about the factories, but then we talked a lot about the traffic, and they were identifying the different traffic patterns, as well as the fact that there really wasn't a lot of people using the bike lanes or bikes or walking either. So to gain a better understanding of air quality around Hopkins, we looked at PM2.5 data using low-cost sensors that Love My Air Wisconsin installed at schools around Milwaukee. So we specifically looked at the one that we installed at Hopkins, and they wanted to identify any trends. And what we saw was, at the time we were looking, a lot of green and yellow. And actually noticing that there seemed to be some higher trends overnight. And so while this was helpful, we wanted to make sure that we were using additional tools to really gain a better understanding of what's going on around this area. And then I want to mention too that simultaneously, as I was joining partner meetings with Hopkins, there was a City of Milwaukee project lead that presented on a reconstruction project, looking to change some of those intersections that I had just mentioned. And so I will refer back to that as we go on. So then we turn to air beams, and which is the palm-sized air sensor that we can use as we walk around, see real-time data. However, we ran into a couple obstacles using the air beams. So this is an example of one of our walks, and it also was following an air quality alert where we had experienced some wildfire smoke in our area. So that didn't really give us a great representation. And then the students went back to school. They had an earlier start time, and then scheduling became a pretty big concern where it was hard to meet with them. So we needed another tool to start thinking through what is going on with the air quality around this area. So that is when I reached out to Tracy and Jenny for some advice and some help. And at first, so we were hoping to kind of look very specifically at specific roads, and through, talking with them, realize that this is more for a bigger picture than just kind of those really very individually focused spots. And so we started including tempo data into our observations, which really was awesome for this group of youth to use and see. And so they started adding some information in, and some key takeaways is that it showed more in the air than just the data from those low-cost sensors. So it really started to build that picture for them, and said of just if there's a green or yellow day. And they noticed that NO2 concentrations are consistently higher during the commute times, and even over some lunch hours some days. And then we discussed how that impacts children's health, especially if those children are going to and from school. And then something that really surprised them and me actually was how much there seemed to be an impact on air quality in Milwaukee from Chicago. On days where we saw those elevated concentrations, you could almost see just kind of this either big blob or like a line directly coming up from Chicago. And so that was really interesting to start to take note of. They're also shocked to see that there were days where there was like the black zone with highest concentrations. And so this has been a really useful tool, and some preliminary feedback right now from the youth is that it was easy to use. It really provided a great visual, and then it helps them share this information out with their community as well. And a fun side note, it was really sweet. At some points, I could tell they weren't looking at the days in our data log, and they were looking up what air quality was like on their birthdays. So it was really sweet. They found it to be a really fun tool. So Amika, Amir, and Laquan truly represent the spirit of faith and service. And every time we meet, even when we just started looking at this at the very beginning of our meetings, their biggest concern is what can we do? If we know air quality is not great in this area, how do we help people? And so they wanted to use this information to make a difference. And so we used information to actually go back and meet with the project lead that was working with the city for the reconstruction project. And they were able to share out information. They were able to ask questions specifically about a spot right in front of Hopkins where there's a lot of cars that idle. And so they came up with some questions and ideas about ways to prevent people from idling right there. And I, again, attribute that to having that tempo image to really see that how much traffic can impact the air quality. And then they also presented their initial data to groups of members after Sunday worship. And they spoke about the air quality data they observed. They even had people download the Love My Air Wisconsin app, which we provide. And then they had recommendations to the members that attended on what they could do to protect themselves. And so the city of Milwaukee will also be coming to do a follow-up presentation with this same group. And so it was a really great way to start connecting all of these different pieces together and really encourage people to have a voice in some of these changes that are coming. So that leads us to the next steps. We're going to continue to meet, but we're looking to continue raising awareness and using Tempo as one of those tools to help us. And if anybody here has more ideas, would love to hear from you all. Thank you.
Thank you, Sarah. Interesting talk. Let's welcome our last speaker, Eladio Knipping from the Electric Power Research Institute. He will talk about some application in the energy.
All right. So I'm here to talk about EPRI. Jenny asked me to talk a little bit about who we are, what we do. I'm going to give an example of where our research is a little bit focused, an example, and then some ideas of how we can engage with this community, which we haven't really been engaging with for many, many years. Not because we haven't wanted to, but our research hasn't really focused a lot on these type of applications of satellite data. So EPRI was founded in 1972. It was really originally developed as an independent R&D organization that received funding from the electric sector, but really operated independently. Over years, it has received funding from diverse sources. It's global. It also receives funding from many government agencies like DOE and EPA. And our mission is to advance safe, reliable, affordable, and clean electricity and energy for society. What does clean mean? Well, clean can be informing standards so that they're adequately set, developing tools like models to implement control strategies to conform and and meet those standards, and also anticipate what potential future issues there may be. And in order to proactively protect human health and the environment. So the program that I lead is called Air Quality Assessments, Multimedia Characterization in Human Health. I also lead the environmental focus on new energy, emerging fuels and technologies, such as hydrogen and carbon capture and storage. So some of the work that we've done includes work with Nathan over here, looking at an exceptional event screening methodologies, nitrogen and sulfur critical loads, so looking at the impact of deposition on the environment, looking at background ozone concentrations, work with DRI, looking at the development of improved models for, for simulation of organic particulate matter or ozone. We actually funded Mike Newchurch to fly over Lake Michigan as part of LM Breeze to capture polluting concentrations and help inform the aroma study. But what I'm going to talk about today is work looking at amine emissions from carbon capture, because I think that'll give you an idea of what EPRI kind of focuses on in the development of our own chemical transport model, a dispersion model that includes photochemistry, which is called SkiChem. We also do health research, epidemiology, and toxicology. The research that we do, we transfer into society in many different ways. We comment on EPA regulations, and we also publish peer-reviewed publications. We do some EPRI reports, but for the majority of what we do, it either goes into regulatory dockets or it goes into the peer-reviewed literature. Oftentimes, even though we don't fund satellite research, we will cite studies that help complement EPRI's own research in those comments that we submit to regulatory dockets. And we use models that are informed by your work, that are constrained and improved by using satellite data like CAMX, and the modeling that we do, for example, to look at the air quality impacts of electrification into the future. So a diverse methodology for knowledge transfer. Shifting to carbon capture is the process by which we're going to capture emissions of CO2 from a power plant or any industrial facility that emits a lot of CO2, and then take that CO2, pass it through an absorber, make a compound, typically with an amine solvent, that then we can take to a stripper, separate out the CO2, compress it, and then transport it into use or storage in an underground cavern or other type of formation. That's carbon capture. The problem here that we are anticipating and doing proactively is what about emissions that come from the absorber of these amine solvents that can lead to the formation of carcinogens, known as nitramines and nitrosamines. So there's chemistry that is known for these, and we have chemistry for some of them already: monoethanolamine, AMP, piperazine, and other solvents. We don't have them all. A lot of the solvents are proprietary, but we can start developing the tools in order to understand what these potential health impacts are. So we have to take into account the plume travel, dispersion, dilution, chemistry deposition of all these constituencies coming out of a power plant or industrial plume. And then we compare it to health guidelines. The one that is most actively used for comparison is from the Norwegian Institute of Public Health of 0.3 nanograms per cubic meter. I wrote it down in micrograms per meter cube just to emphasize how small the concentration needs to be in order to reach a level of a health concern. 0.3 nanograms per cubic meter. What we use is the SkiChem model in order to simulate that. That model includes the chemistry that is used in chemical transport models such as CAMX, CMAC, GeoSchem. All of these models have been validated with the use of satellite data. So there is an indirect application of satellite data when we use these models. And the SkiChem model has ozone and OH formation Interestingly, it needs background concentrations of everything in the atmosphere so that that plume can evolve and react with the background and form the nitrosamines. It needs to have ozone, it needs to have OH, and that comes from a full chemical transport model simulation. So it treats PM chemistry, it treats ozone chemistry, it treats absolutely everything, and it starts forming these nitrosamines and nitramines. So what we found when we did our simulation is that if you start looking at the formation of nitrosamines and nitramines from an uncontrolled stack, you are going to exceed that level of concern. 0.3 nanograms per cubic meter, you're actually going to be 4 times as high, 1.34 nanograms per cubic meter. That's concerning. But we're being proactive here. So we can tell the developers of the absorber that they need controls. They need an acid wash in order to constrain those emissions, to make sure that they don't reach those levels of concern. And then properly designed absorber with an acid wash can knock down those emissions and then reach a concentration in the atmosphere way below that 0.3 nanograms per cubic meter. Actually, for this simulation, it became 0.07 nanograms per cubic meter. So we're no longer in that area of concern. Again, these are the types of issues that EPRI is looking at these days. Not trying to just let the technologies develop on their own, but having input into the development of the technologies so that we can anticipate and avoid potential health impacts and environmental impacts. The model also looked at ammonia emissions coming from the facility, and that ammonia was forming particulate matter, fine particulate matter, up to about 1.2 micrograms per cubic meter. We were able to knock down those ammonia emissions in our simulations and also reach a factor of 4 reduction, so 0.3 micrograms per cubic meter. Is that enough when we look at fine particulate matter? Don't know. We would have to look at what the levels of PM are in those regions and then see if we are going to exceed that lower 9 micrograms per meter cube NACs by adding these 0.3 micrograms per cubic meter. That's where we need your information. We need better information of what these background concentrations are in order to make sure that we are not exceeding levels of health concern based on the NACs. So how can we use satellite data for electric sector needs? I think we use them for assessments, regulatory analysis, and implementation of standards. We've already seen and commented on within EPRI comments just the value of the effectiveness of control strategies coming from satellite data, the contributions from other sectors, the contributions of biogenic and soil emissions, and also changes in the chemical regimes. So looking at trends, contributions, and sensitivities. But when I start thinking about how am I going to work with you guys, and I want to make sure that I understand what the global and regional background concentrations are, using cutting-edge machine learning and AI methods to improve sector-specific contributions to emission inventories. Be able, again, as emissions go down, the biogenic and the soil inventories become more and more important. Assess cross-state air pollution contributions. This is critical. As ozone and PM standards go down, states are required to control their emissions upwind, downwind. So that's going to be important. Using models is important, but they need to be constrained with the data in order to make sure that we're reaching valid conclusions. And then, Nathan, we need to continue working on exceptional event demonstrations. And this is the community that we need to be working with. And you already are. And these are not future applications for you. This is what you're already doing. This is future applications for EPRI to work with you. So that's where I see the potential role. And Tracy, thank you for reminding me because I'm excited here.
Let's invite all of our speakers back to the front. Okay, then I think we can start our Q&A session. Does anyone have any question for any speaker? Okay, go ahead.
I have a question for Chen. Thank you for your wonderful talk. I was just wondering, for PM1, which anthropogenic source do you think
will be effective control. And also, for it to be policy relevant, you need a ground-based measurement of PN1. And how do you think that can be overcome? Do you think state governments would have to invest in new instruments, or they could possibly rely on this data that you produced?
Yeah, thanks for that question. So as you see from the scatter plots that we have the mass ratio that these inorganic and organic components have mass ratios that are higher than 0.75, 0.8, 0.9. So dominantly, these species are relevant definitely for PM1. So sources contributing to secondary inorganics and organic aerosol will be responsible for PM1 dominantly. But the benefit of PM1 is that it has less contributed, much less contributed by mineral dust in the sea salt, for example. So that's for question one. For the second question, so I don't remember the second question. Please repeat.
So I see the relevance of PM1, and I wish future trajectory, we can target PM1 as well. But
Right.
do you think for us to do that, each state would have to purchase separate instruments to do that?
Yeah, so that's exactly the purpose of that wheel that I illustrated in the last slide, for example. So I believe that is an important and additional metric for air quality. And by producing this data set first, we hopefully would drive up the findings about its health relevance, and that would possibly motivate more monitoring efforts, such as you introduced. So hopefully this meeting would promote the usage of this data as a very suitable platform. Thank you very much.
Okay, thank you. Any more?
This is a question for Randall. Is the Modus MAIAC product being totally replaced by VIIRS soon?
Thank you for that question. What we do is endeavor to represent all of the aerosol optical depth observations available to us over that time period from 1998 when it starts to the present. So what we have is a period historically where we would have Modus, and then subsequently we would have VIIRS, and in the middle we would have a transition period. So as the VIIRS MIAC data become more available, and that's a very new product, MIAC is key for us because of both its fine resolution of 1 kilometer as well as its quality, then we'll see a transition between the two. But we try to avoid a step function as we transition and rather just examine the consistency of those two data sets during the transition period so that it can be a smooth transition from a historical data set to the more recent one. Thank you.
Yeah, Leif Paulson with Wyoming DEQ. For Chi, getting back to the question that was just asked a minute ago on the ground-based measurements for PM1, has there been any consideration to low-cost sensors like the Purple Airs or medium-cost sensors like Modulaire or Quantaq's Modulaire instruments to investigate PM1 from the ground level?
Yeah, that's a great question. So I personally believe that low-cost sensors are better suited for PM1 than PM2.5 because for PM2.5 calibration, what I see from literature is that they usually need to distinguish dust polluted versus dust-free conditions. But the dilemma right now is that most people are focusing on calibrating PM2.5 using this existing archive low-cost sensor. I hope that with the emergence of these estimates and with the emergence of possibly identified health outcome, it will encourage more people to give attention to the calibration of this existing wealth of data set for PM1, which might be more directly related compared to PM2.5. And that's definitely something that is promising to survive the ground-based monitoring of PM1. Thank you very much.
Thank you all for a great panel. Great to hear your talks. And my question is mainly for Sarah and Eladio. Both of you presented really like exciting examples of how far the applications of satellite data and related work can reach, whether it's to high schoolers in a church and their public outreach applications, or to industry groups that are thinking about the broader regulatory context and problems that don't even quite yet exist around like a means. And I guess, one challenge that we sometimes face on the satellite applications is, where is it best to work with trusted intermediary organizations like EPRI, like Children's Health of Wisconsin? And what is the role of NASA and NASA-funded efforts directly? And actually, I had one NASA colleague who made the point that NASA works retail and wholesale, that you can go direct to the NASA websites, but also a key part is working with intermediary organizations. And I'm curious, like in both of your very different audiences, where do you see actions that NASA can take to better be a deliverer of information? And where do you see that really don't worry about being direct to consumer, just work with us or work with other partner organizations?
Great question. Do you want to go first? I'd have to think about that a little bit. I would say I'm excited about the workshop this afternoon, because for me, my background's not air quality. So I'm having to learn some pretty scientific language applications, things like that, that it's new to me. So, and actually it's a very good point of part of my interest too in working with such a small group is that we're branching into high schools this year. Previously, our last 2 years, we're in a 3-year grant. We're extending, but our first 2 years were kind of the elementary 8th grade. And so this is our first year really getting into high school. And I wanted to have experience working with this tool. So as I'm sharing this, these different opportunities of working with PM2.5 from low-cost sensors, and then using this as another tool, I wanted to know how does this work? What do I need to say? What does this mean? I've already had some teachers asking me some very specific questions. So I'm excited to be at this workshop this afternoon. I think that's a huge piece that is going to help me promote this and also know how it should be used by community members. And I see that as kind of being that great, as you have put it, bridge of I can learn this and then I can take it, even break it down even further. I have a teaching sheet I made that is literally step-by-step how to go to the Tempo site, and then, just a very great visual step-by-step way of using Tempo's website. And so that's how I see my role, is kind of being that in between of learning some of these really technical things, but then communicating in a way so that, and I have that vision, that perspective too, because I had to teach it to myself, or I was working with you guys. So I know the questions, I kind of know where the gaps are, and then I can try to fill that even further. Oh, sorry.
I think it comes down to building trust. For industry, and we're not industry, we work with industry, it's all about making sure that it's effective. Whether the standard setting process is effective and protective of public health, whether it is the implementation of that standard, the tools that are used, the approaches, the control strategies that are ultimately developed, they need to be set with sound, fundamental, objective science that can be trustworthy. And you folks do work that that we sometimes look at and challenge at EPRI. Not necessarily in the satellite world, but we do complementary science because we feel like, well, how about this? And have you looked at something else? Improving the mission inventories, improving the modeling tools so that they're more accurate in order to develop those strategies for cross-state transport. So it comes down to building trust. And that's where, everyone can agree. I don't think anyone will disagree that what we need is trustworthy tools that are effective. Doesn't mean that we have to delay action, but we continuously improve. That's why HAQAST has lasted, decades, because science evolves, our understanding evolves, and that trustworthiness continues to be fundamentally shaped through emerging science.
Thank you. Any more?
We have a couple of questions online. And also, I just want to say for me to you guys that thank you so much for your talks. It's really interesting to hear and really interesting to see the diversity of applications that we can do with this and the cutting edge science. So just a couple of questions from our online audience. For Dr. Lee, is the PM1 dataset publicly available? Or if not, could you share on how to request that?
So if you check our paper, it will be fully open access after September 2026. For now, there is a small embargoing period. Feel free to contact us if your application fits in, maybe an early access might be possible. Thank you.
And I can help share your email with the HAQAST folks who registered. We have another question. Does Tempo provide ground level PM2.5 estimates yet? Do you want to answer that? How's it my note? Not yet. Soon. Okay. You heard it here. Yes, and there's been a lot of discussion on PM1 and the regulatory implications and different ways to measure. So I think people have been very interested in that too. So I just wanted to convey some of that conversation here.
Hi, I'm from the community member, and I'm honored to be allowed in this conference. My question is for Mr. Knipping. Yes. You talked about underground storage as an important part of your recover of carbon. And I was wondering what the impact of the underground emissions have on the environment.
So any emissions from storage would be CO2 emissions. And what we're looking at, not at EPRI, but elsewhere, once the CO2 is stored underground, there's really a very low possibility that any of that CO2 will emerge. It's really during the transport, making sure that there are no leakages during transport. That's a higher likelihood, low, and making sure that those unintended releases are avoided through proper material development and handling.
But what is the long term of the underground storage?
I don't have an answer to that. I will get you an answer though. I will follow up.
Okay.
Thank you, everyone. Those were all great talks. I have a question about the PM1 as well. Specifically, so you used case studies to kind of get the PM2.5 to PM1 ratios or the K values. I was wondering if those varied a lot across cities, or if you have to, how many case studies did you have to use? Did you interpolate that across the United States, or just how did those K values vary? Thank you.
So at this stage and at this data availability that we have, we use component fixed ratio. So for each of the 7 major components, we have a fixed ratio. And that ratio do vary spatially and temporally. when the composition changes spatially and temporally. Thank you.
That makes sense. Thank you.
So I wanted to pick up on something that Eladio said about trustworthy research and trust. And this is for anybody on the group, but I'm thinking both Eladio, of course, and also Randall, because, over the past 50 years in atmospheric science, atmospheric chemistry, there's been a big shift where back in the 70s and 80s, which was before I was in the field, there was a lot of research from industry groups, Dow Chemical, Ford Motor, electric utilities. And in fact, like earlier this summer, I attended the Gordon Research Conference for Atmospheric Chemistry, and I talked to my advisor, Chip Levy, who was in the field at that time. And he said that the Gordon Research Conferences used to be primarily industry representatives. But it's really shifted with so much of the research being funded by federal organizations, and including NSF and EPA and NOAA and NASA and USDA. There's a lot of federal agencies that orbit in the air quality space. And I guess I'm curious, like, I think what you're saying, EPRI doing to have a voice that is trusted by different constituencies so that the science doesn't get polarized, or at least that there's sort of a view of trustworthy alternate perspectives. I guess I'm curious from your perspective, like, do you see that maybe that's something that industries are interested in funding more, and especially with changes in the federal landscape of funding? And I mean, I guess maybe I'll just say, like, Randall's data and his team's data is used all around the world by so many groups. And it just this idea that, like, it's the kind of information that could be funded by industry organizations, but there's not right now like a clear, there's no solicitations coming from industry groups in the same way that there are the federal government. And I guess I'm curious if you want to like expound on your opinions about industry funded research by EPRI, by universities, by the changing landscape of the past and the present. I just feel like we're at a moment of change, and a lot of your comments seem to kind of resonate with that.
So the 70s and 80s, I mean, that's pre-Clean Air Act of 1990. So there was a lot of research going on that would eventually inform the acid rain program, that would eventually support the regional haze rule or the setting of the ozone standards. Remember that it was photooxidants and still is technically, but we went from a 1-hour standard to an 8-hour standard. We added PM2.5. I don't know if we're ever going to add PM1, by the way. Be a large hurdle there as a standard itself, but we may. And so emissions were much more. So there was a lot at stake, right? Now the focus with the compliance with things like CASPER, the acid rain program, being completed, state implementation plans, CASPER, the cross state air pollution rule, looking at secondary standards. There's if a compliance bias, just tell us what the standard is and we'll do what is necessary, and we'll fund, different activities in order to help us understand the best control strategies that will be effective across different sectors. More so than the fundamental science that was being funded in the 70s and 80s. So I think that there's just been a shift from one urgency to the other. With the advent of new fuels and technologies, and the rising need for electricity due to data centers, we may see a shift once again, particularly in permitting, in needing fundamental science for compliance with permits, making sure that you're not exacerbating any local and regional air quality, of course. And these community concerns, I think they're going to drive a lot of work. So I think that we may see an uptick in research from industry overall, not just the electric industry or the energy industry, in order to address these concerns.
Yeah, thanks, Tracy, for that great question. And I'll build on what we just heard from Eladio and talk about industry from a data-driven perspective. I think we're seeing a lot of innovation in this space, both in the availability of machine learning algorithms that are being developed, perhaps funding universities, but perhaps on their own. We see evidence of some very large entities, Google, for example, or others that are getting involved in the environmental data space. That's a very active area of growth in which powerful computing facilities offer a real advantage for those. And then we're seeing spin-offs from those organizations, such as AWS has a philanthropic arm that we're grateful for its support that is enabling dissemination of data at the global scale across the geochem community, as well as on satellite-derived PM2.5 data and providing access to computing. So I'm seeing growth in this space, and I think those partnerships can be incredibly powerful. And we're seeing participation by those large entities in scientific conferences as well that are really exciting to see. Do you have something you'd like to say? No?
Okay, thank you. Any more?
One more comment. I just want to thank all you scientists for all the wonderful work you've done. I appear to be a lot older than most of you, so I grew up in the 50s in Los Angeles, and it was terrible. I have health issues because of the pollution, and it's just so much better, and I want to thank you very much.
Okay, any more questions? Then I will have a question about the satellite data for Sarah and Eladio. Could you talk a little bit more about how do you apply satellite data in your analysis or your modeling? And what's the most difficulty you meet to use those satellite data?
The use of satellite data through every research has not been as robust as I would want it to. There was work that we did with Ted Russell and Talat a while back using a fused surfaces, model and measurement and satellite data to look at conclusions that would be driven from epidemiology. So we did some work on that. We've helped support the development in the past of the geochem model, which is constrained by satellite data for model performance. But basically, my last slide, I think we need to do more, and we still have exceedances of the standards, and some of these are challenging. And when we rely only on monitoring data or infrequent campaigns, which are useful, I mean, they certainly are. We're talking about sparse or intermittent data sets. The satellites are there. I mean, they're telling us what's going on day after day after day. We need to leverage that, and coming to this community and talking and hearing what you folks are going to talk about is going to inspire me to go back and say, we need to work more closely with you.
I would say some like cloud coverage, like that's just, but that can't be, adjusted. There are some days where we're like, oh, like we really want to know what the satellite found, and there's cloud coverage, so that happens. But then, just really the application, as kind of breaking it down to the simplest terms as possible. you know, the students and I were looking at, we like zoomed in. And so at first, when we were looking at the PM2.5 sensor, we would look at what was the color in that, like in our very small area. And then on those days where we noticed higher concentrations, we would zoom out to have a bigger understanding. But I'm learning alongside them in a sense right now as well. So we're kind of learning as we go. And I think I really appreciated the comment on trust, because especially for some of these communities that we are having the most concerns for, and as I mentioned in even my presentation, like from the beginning, even, I mean, the youth were like, what are we going to do with this? Like, how are we going to actually help people? And so we've talked a lot about that. And so I think just even coming up with additional ideas from experts of like, how can we use this to drive action would be really helpful. So I can come back with more answers later as I learn more.
Okay, thank you.
And one thing, just off the cuff, Tracy, I graduated in 2002. We're contemporaries. You know, we're not. We're children of the 70s and 80s. And when I started looking at satellite data at that time, I was like, "Is this going to be useful?" I mean, the way that the acceleration in this field, in just resolution and species, quality. Yes, there are challenges, but the advancements that have been made through instrument has been phenomenal. So yeah, you are trustworthy.
Okay, thank you. Any more questions or comments? Okay. Okay, perfect, Tim. Time. Yeah, thank you for everyone to join this session. And thanks for all of our speakers here.